Hello everyone, welcome to this course on basics of electronics. I think you all are safe and healthy with your parents at your home. This is my 6th video lecture on my YouTube channel Maulik Takniki and Adharbut Vigyan. In this video lecture, we are going to talk about basics of operational amplifier, and in upcoming videos, we will talk more about operational amplifier. An operational amplifier or op-amp is a very high gain, high input resistance and directly coupled negative feedback amplifier which can amplify signals having frequency ranging from 0 Hz to a little beyond 1 MHz. It was originally designed to perform mathematical operations like summation, subtraction, multiplication, differentiation, and integration. That's why it is called operational amplifier. It is basically a 3-terminal device which consists of 2 high impedance inputs. One of the input is called the inverting input, which is marked with a negative or minus sign. The other input is called the non-inverting input, which is marked with a positive or plus sign. You can see the block diagram of an operational amplifier on the screen along with its IC. The standard triangular symbol of an op-amp is shown in the above figure. All operational amplifiers have minimum 5 terminals: inverting input terminal, non-inverting input terminal, output terminal, positive bias supply terminal, negative bias supply terminal. When a signal applied at negative input terminal, means at inverting terminal, it will appear amplified, but its phase will be inverted at the output terminal, as you can see on the screen. When a signal applied at the positive input terminal, means at non-inverting terminal, it will appear amplified and its phase will be same at the output terminal, as you can see on the screen. It means that the input terminals which is marked with minus and plus signs only indicate the inverting and non-inverting terminals. It does not imply that a positive input voltage has to be connected to the plus marked terminal and negative input voltage to the negative marked terminal. Now, characteristics of operational amplifier. Its open loop gain is infinity. Its input resistance is infinity. It has very low output resistance, approximately equal to 0, and it has very high bandwidth. Now, applications of op-amp. Operational amplifier can be used as an unity follower. It can be used as an adder or summer. It can be used as a subtractor. It can be used as an integrator, as a differentiator, and as a comparator. Now, op-amp as an unity follower. You can see the figure or the block diagram of a unity follower on the screen. It is called unity follower because it provides a gain of unity without any phase reversal. It is also known as a unity gain amplifier, a voltage buffer, or an isolation amplifier. It allows input voltage to be transferred as output voltage while at the same time preventing load resistance from loading down the input source. It is due to the fact that its input impedance is very high and output impedance is 0. In a voltage follower circuit, the output voltage is equal to the input voltage. Thus, it has a gain of 1, means unity, and does not amplify the incoming signal. Now, op-amp as an adder or summer. You can see the block diagram of adder or summer using operational amplifier. This adder circuit provides an output voltage which is proportional to or equal to the algebraic sum of two or more input voltages, each multiplied by a constant gain factor. The circuit shown in the above figure is inverting adder circuit. Calculation. We will consider point X as a virtual ground. Okay. Now I1 from Ohm's law, I1 is equal to V1 upon R1, I2 is equal to V2 upon R2, I3 is equal to V3 upon R3, and I is equal to minus of V output upon RF. Now applying KCL to point X, we have I1 plus I2 plus I3 plus minus I is equal to 0. Or from Ohm's law, on the place of I1 we can write V1 upon R1 plus on the place of I2 V2 upon R2, V3 upon R3 minus in bracket minus V0 upon RF is equal to 0. So V1 upon R1 plus V2 upon R2 plus V3 upon R3 plus V output upon RF is equal to 0. Multiplying by RF in both sides, when we multiply we get this value, and after calculation we get the value V0 is equal to minus of K1 V1 plus K2 V2 plus K3 V3, where K is equal to RF upon R. The overall negative sign is unavoidable because we are using the inverting input terminal. If R1 is equal to R2 is equal to R3 is equal to R, then V0 is equal to minus of RF upon R into V1 plus V2 plus V3, or V is equal to V output is equal to minus of K V1 plus V2 plus V3. Hence output voltage is proportional to the algebraic sum of the three input voltages. If RF is equal to R, then output exactly equals the sum of inputs. However, if RF is equal to R upon 3, then V output is equal to minus of 1 upon 3 V1 plus V2 plus V3. Obviously, the output is equal to the average of the three inputs.